Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by triangle ABC. And in the second question, we'll find out the area of the blue triangle that is inscribed by the quarter circle. Okay, so we'll start with the first question. In the drawing, we have triangle ABC. Angle ABC equals to 90 degrees. Side AB equals to 8 units. And we want to find out the radius of this circle that is inscribed by triangle ABC. And we also know that BC and AC, the lengths of BC and AC are integer numbers. Okay, and we want to find out the radius of this circle that is inscribed by triangle ABC. The right triangle, triangle ABC. So, first of all, we will define side BC of the right triangle, triangle ABC as A. BC equals to A according to our definition. And we'll define the hypotenuse AC as B. That is to say, the length of the hypotenuse AC is equal to B units according to our definition. And we have the Pythagoras theorem. So we will implement the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem in the right triangle, triangle ABC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here, by PT is a relation for Pythagoras theorem. So, the hypotenuse is AC, therefore the square of the hypotenuse is AC squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB squared plus BC squared. I'll repeat again. In the right triangle, triangle ABC, according to the Pythagoras theorem, we get that AC squared equals to AB squared plus BC squared. This is equation number 1. So, according to our definition, AC equals to B. Therefore, AC squared will be equal to B squared. And it is equal to AB squared. AB is 8, so AB squared is 8 squared, that is 64. Plus BC squared. According to our definition, BC equals to A. Therefore, BC squared is A squared, so it is 64 plus A squared. Here we will subtract A squared from this equation, equation number 1. And we get that according to equation number 1, B squared minus A squared equals to 64. Okay, so here we have the algebraic identity that states that B squared minus A squared equals to B plus A times B minus A, and it is equal to 64. So actually, we know, according to what is given as the question, BC and AC are integers. I'll write it down here. Side BC and the length of side BC and the length of side AC of triangle ABC, the right triangle ABC, it is integer number. So they are integers. So BC equals to A and AC equals to B, therefore we can say that A and B are integers according to what is given as the question. But because of the fact that A and B are the lengths of triangle ABC, they are lengths, and therefore they must be positive numbers. Therefore they are positive. So in conclusion, so we know that A and B, from those two lines, we can conclude that A and B are positive integers. Okay? Because here, from here we have A, B, and they are integers, and from here we know that AB must be a positive. So from those two lines we conclude that A and B must be positive integers. Okay, so we can write down here that A and B must be positive integers. They are positive integers. And because of the fact that A and B are positive integers, it means that A plus B must be greater than A minus B. Because when you have positive integers and you add two numbers, it will always be greater than the subtraction of those two numbers. Therefore, A plus B must be greater than A minus B. And because of the fact that here AC equals to B, AC is the hypotenuse. The hypotenuse is always greater than the perpendicular that is A. So the hypotenuse B must be greater than the perpendicular A. Okay, so we can write here that the hypotenuse B must be greater than the perpendicular A. So B is greater than A. If we subtract from this inequality A, we will get that B minus A is greater than 0. So B minus A is positive, and we know that B and A are positive integers. Therefore, B minus A, it must be a positive integer. Here, B minus A must be a positive integer. And A is a positive integer, B is a positive integer. When you add two positive integers to each other, the result must be a positive integer. So A plus B is also a positive integer. Okay, A plus B is also a positive integer, and A minus B, it is also a positive integer. So here we have, according to equation number 1, B plus A times B minus A equals to 64. We have already found out that b plus a must be a positive integer, and b minus a also must be a positive integer. Okay? So here we have to find out two positive integers that when we multiply them by each other will give us 64. Which two positive integers we have that when we multiply them by each other will give us 64? There is very limited option that we have here. It is very limited options. The first option is 1 times 64 will give us 64. Okay? 1 times 64 will give us 64. Also, 2 times 32 will give us 64. And 4 times 16 also give us 64. 8 times 8 also give us 64. 16 times 4 also give us 64. 32 times 2 also give us 64. And finally, 64 times 1 also give us 64. So actually we have 1, 2, 3, 4, 5, 6, 7 options. We have only 7 options that when we multiply two positive integers, that can give us 64. Okay? So, according to what we have already found out, we know that a plus b, it is also b plus a, it is greater than a minus b. So it means that the first column must be greater than the second column. Why? Because b minus a is greater than b plus a is greater than b minus a. And 1 is less than 64, therefore it is not true here, because b plus a must be greater than b minus a, so 1 is not greater than 64. Therefore, this option is invalid option. We will cancel this solution. 2 is less than 32. Therefore, we will cancel this solution. This is not valid solution. 4 is less than 16. Therefore, we will cancel this solution. It is invalid solution. 8 is not greater than 8. Therefore, it is invalid solution. 16 is greater than 4. Therefore, this solution is possible solution, and 32 is also greater than 2. Therefore, this is also a possible solution. And we also know that 64 is greater than 1. This is also a possible solution. But in the next step, we will add the two numbers together. That is to say, we will add b plus a to b minus a, and we will analyze the solution. What is b plus a plus b minus a? Here, when we add the two numbers together, b plus a to b minus a, b plus b is 2b, and a minus a is 0. So in conclusion, we found out that when we add the two numbers together, we got 2b. But 2b, we know that b is a positive integer. If b is a positive integer, then 2b is even number. 2b is an even number. That is to say, when we add the two numbers together, we have to get an even number. Okay, so if we get an odd number, it is invalid solution, because here we can see that 2b, b plus a plus b minus a is 2b. It is even number. It is even number because b is a positive integer and 2b must be even number. Therefore, any odd number is incorrect solution. So we have three options to analyze. Here, b plus a plus b minus a. b plus a is 16 and b minus a is 4. So 16 plus 4 is 20, as 20 is even number. So this solution is correct solution. 32 plus 2 is 34, and 34 is even number. So this is correct solution. While 64 plus 1 is 65, and 65 is odd number. And we must to get an even number. When we add the two numbers together, we must get an even number. 2b is even number, and 65 is odd number. Therefore, this solution is incorrect solution. So in conclusion, we left only with two solutions that are possible for the length of the hypotenuse no, it is not the length of the hypotenuse, but it is b plus a and b minus a. Okay, so here we will find out the values of a and b, that they are perpendicular on the hypotenuse of the right triangle ABC, but we just have here b plus a and b minus a. So according to the first solution, we have b plus a equals to 16, while b minus a equals to 4. This is the first solution. And according to the second solution, we have b plus a, according to the second solution, b plus a is 32, while b minus a is 2. b minus a is 2. So here we will add those two equations together. b plus a plus b minus a. Here b plus b is 2b, and a minus a is 0. And here 16 plus 4 is 20. So in conclusion, we found out that 2b equals to 20. Here we will divide this equation by 2, and we'll get that b equals to 20 over 2, that is 10. b equals to 10 units, that is to say, according to this solution, b is the hypotenuse, and the hypotenuse of the right triangle ABC equals to 10 units. We already know that one perpendicular equals to 8 units. Now we'll find out the value of a, that is the second perpendicular. So here we know that b equals to 10 units according to the first solution, and we have the equation that b plus a equals to 16. b plus a equals to 16. We'll subtract b from this equation, and we get that a equals to 16 minus b. So a equals to 16, and we already found out that b equals to 10, so we substitute b by 10. So it is 16 minus 10. A equals to 16 minus 10, that is 6. So we found out that a equals to 6. In conclusion, we found out that the hypotenuse b equals to 10 units, and the perpendicular BC equals to 6 units according to the first solution. I write here, according to this solution, A equals to 6 units, that is the length of the hypotenuse, the length of the perpendicular, and the hypotenuse B equals to 10 units according to the first solution, and according to the second solution, b plus a equals to 32, while b minus a equals to 2. Here we read those two equations together. B plus b is 2b, and a minus a is 0. So 2b equals to 32 plus 2, that is 34. 2b equals to 34, we'll divide this equation by 2, and we'll get that the hypotenuse b of the right triangle ABC equals to 34 over 2 is 17. The hypotenuse b equals to 17 units according to the second solution. And here we have b plus a equals to 32. We subtract b from this equation, and we get that a equals to 32 minus b. And we've already found out that b equals to 17, so we'll substitute b by 17, and we'll get that a equals to 32 minus 17, that is 15 units. In conclusion, we found out that according to the second solution, the perpendicular A equals to 15 units, while the hypotenuse B of the right triangle ABC equals to 17 units. So actually, we can draw the two right triangles, the two solutions to the question. We have the two solutions to the question. According to the first solution, first of all, we know that one hypotenuse of the right triangle ABC equals to 8 units. It is given as the question. Okay? And we also here find out that the second one perpendicular is 8 units, the second perpendicular is 6 units. The second perpendicular is 6 units, and the hypotenuse equals to 10 units. This is the right triangle ABC, but you should remember that that is not the question that we have been asked here. We want to find out, here the hypotenuse is 10 units, we want to find out actually the radius of the circle that is inscribed by this right triangle, triangle ABC. Okay, we have inside this triangle ABC a circle that is inscribed, and we want to find out the radius of this circle. Okay, so we haven't found the answer to the question yet. You should remember that this is not the answer to the question. Okay, and the second solution to the question is that the right triangle ABC, it is equal to, we have one perpendicular that is equal to 8 units. It is given as the question. And the second perpendicular equals to 15 units. Here BC equals to 15 units, and the hypotenuse equals to AC equals to 17 units. And you should remember that the question is to find out the radius of this circle that is inscribed by triangle ABC. We want to find out the radius of this circle that is inscribed by triangle ABC. Okay, we have this radius that is equal to capital R, and we want to find out the length of the radius that is inscribed by this triangle, triangle ABC. That is to say, to find out the length of the value of capital R. Okay, so Here we have so actually if we have a right triangle, any right triangle, that we actually know that the size of side AB equals to A units in its length. And we also know that the length of side BC equals to B units in its length. And the length of the hypotenuse AC is C units. Okay? So we have here triangle ABC, right triangle, triangle ABC. The length of side AB is A units, the length of side BC is B units, and the length of the hypotenuse AC is C units. Okay? So actually, we have rule number 1. Here we define the center of this circle is point O. And we have rule number 1 that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. Again, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. We define the point of tendency of tangent BC with this circle as N. We will join here, we'll define the point of tendency of tangent AC with this circle as M. We'll join points M and O together by a straight line. What is the definition of line segment MO? O is the center of the circle. Okay, O is the center of the circle according to our definition. M is the point of the circle itself. This is exactly the definition of a radius. That is to say, MO is the radius of this circle. That is to say, it is equal to capital R. Okay. Here we will define the point of tangency of tangent AC with this circle as Z. So according to rule number 1, we have here the radius OM. The radius OM, it is drawn to the point of tendency. That is to say, it is drawn to point M. That is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then this angle, the tangent AB will be perpendicular to the radius MO. Again, tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Likewise, we have here the radius ON that is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, it means that this angle equals to 90 degrees. And this angle will be equal to 90 degrees according to rule number 1. So actually, in quadrilateral NOBN, we have 1, 2, 3 right angles. And the sum of right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle MON. In total, the sum of those 4 angles must be equal to 360 degrees. And if we subtract 270 degrees from the equation, we get that the missing angle, angle MON, equals to 90 degrees. So this angle equals to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So this angle must be equal to 90 degrees in order to complete the sum of the angles in quadrilateral MO and B to 360 degrees. Okay, actually we have another rule that is actually rule number 2. According to rule number 2, a tangent to a circle, according to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Again, the lengths of two tangents from a common external point to a circle are equal. Okay? But before that, we will return to quadrilateral MO and B, because of the fact that in quadrilateral MO and B we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. That is to say, in rectangle MO and B, NO must be equal to MB. NO must be equal to MB, but NO equals to R. Therefore, MB must be also equal to R. Okay? B must be also equal to R, that is the radius of the circle. Likewise, according to the same rule that the opposite sides of rectangle are equal to each other, we will get that MO equals to BN. MO equals to BN, but MO equals to R. So, from the fact that MO equals to R, therefore BN also equals to R, because of the fact that MO equals to BN. Okay, so actually found out that quadrilateral MOBN is a square because all of its sides are equal to each other. So here, what is the length of AM? AM equals to AB minus MB. AM equals to AB minus MB. That is to say, AM equals to AB, that is A, minus MB, that is R. So in conclusion, we found out that AM equals to A minus R. The length of AM equals to A minus R. In the next step, I will present to you. But before that, here we have what is the length of NC. Here it is very easy to see from the drawing that NC equals to BC minus NC. BC minus BN equals to NC again. BC minus BN equals to NC. That is to say BC equals to BC, that is B, minus BN, that is R. So in conclusion, NC equals to B minus R. Okay? NC equals to B minus R. So in the next step, I will present to you rule number 2 that I have already mentioned 2 minutes ago. The lengths of two tangents from a common external point to a circle are equal. The lengths of two tangents from a common external point to a circle are equal. So if we focus on the common external point, point A, we have two tangents to this circle, tangent AM and tangent AZ. And according to rule number 2, they are equal to each other. That is to say, AM equals to AZ. AM equals to AZ according to rule number 2. But AM equals to A minus R. Therefore, AZ must be also equal to A minus R. AZ must be also equal to A minus R. In the next step, we will focus on the common external point, point C. From the common external point, point C, we have two tangents to this circle. We have tangent CN and we have tangent CZ. And according to rule number 2, they must be equal to each other by their lengths. That is to say, CN equals to CZ, according to rule number 2. but CN equals to B minus R. Therefore, CZ must be also equal to B minus R. Okay, CZ must be also equal to B minus R. So, what is the length of the hypotenuse AC? The length of the hypotenuse AC, it is equal to here AC equals to AZ plus ZC. Okay, I'll write it down. The length of the hypotenuse AC, from the drawing it is very easy to see that AC equals to AZ plus ZC. AC equals to AZ plus ZC. AC equals to C according to our definition, so we'll substitute AC by C. AZ equals to A minus R, according to what we have already found out, while ZC equals to B minus R. So in conclusion, we found out that C equals to A minus R plus B minus R. That is to say, C equals to A plus B minus R is minus 2R. So in conclusion, we found out that C equals to A plus B minus 2R. Here we will add 2R to this equation, and we will get that 2R plus C equals to A plus B. Here we subtract C from this equation, and we get that 2R equals to A plus B minus C. So here we will divide this equation by 2, and we will get that the radius that we are looking for, that is actually the radius of the circle that is inscribed by the right triangle ABC. Here we have the right triangle ABC, and inside the right triangle ABC we have this circle that is inscribed by the right triangle. Okay, so the radius of this circle, it is equal to A plus B, that is the sum of its hypotenuse, that is the sum of its perpendiculars, minus the hypotenuse C over 2. I'll repeat again, that the radius of this circle that is inscribed by the right triangle ABC equals to the sum of its perpendiculars, that is actually A plus B, minus the hypotenuse that is C over 2. Okay? So actually, we have already drawn the two solutions to the question. Here, we will use this formula that we found out from finding out the radius of this circle that is inscribed by the right triangle ABC. The radius equals to A plus B, that is the sum of its perpendiculars, minus the length of the hypotenuse over 2. So here, we'll get that the radius of this circle that is inscribed by triangle ABC equals to the sum of its perpendiculars, that is 8 plus 6, minus the length of the hypotenuse, that is 10 over 2. So the radius of this circle that is inscribed by the right triangle ABC equals to 8 plus 6, that is 14, and 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle that is inscribed by the right triangle ABC equals to 2 units. Now, according to the second solution, we found this triangle. We will use the same formula to find out the radius of this circle that is inscribed by the right triangle ABC. The radius of this circle equals to the sum of its perpendiculars, that is 8 plus 15, minus the hypotenuse, that is 17 over 2. 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So we found out that the radius of this circle equals to 3 units. So in conclusion, we actually found out that we have two answers to this question. The radius of this circle that is inscribed by the right triangle, triangle ABC, will be equal to either 2 units or 3 units. Okay, that is the answer to the question. The radius of this circle that is inscribed by the right triangle, triangle ABC, it is equal to either 2 units or 3 units. So we finished with the first question. In the next step I will present to you the second question, and we will solve the second question in 2 different methods. Okay. So in the drawing we have a quarter circle, and we know that AD equals to DO. AOB is a quarter circle, AD equals to DO. We also know that side OB or BO equals to 2 units. Inside this quarter circle we have the right triangle, triangle DCB that is inscribed by the quarter circle, and we want to find out the area of this blue right triangle, triangle DCB. Angle DCB is equals to 90 degrees, therefore triangle DCB is a right triangle. So first of all, because of the fact that AOB is a quarter circle, it means that point O is the center of the quarter circle, and then angle AOB equals to 90 degrees. And actually, AO, it is also the radius of the quarter circle. So actually, here AO equals to OB. AO equals to OB, and it is the radius of the quarter circle, and it is given us in the question that is equal to 2 units. So AO equals to OB equals to 2, and here we will define AD equals to DO. So we will define AD as X, AD equals to X. So if AD equals to X, then DO also equals to X. And according to what is given in the question, we know that AD plus DO equals to AO. That is to say, X plus X equals to AO. AO, but because of the fact that AO is the radius of the circle, it is equal to 2 units. So X plus X equals to 2X, that is 2. 2X equals to 2. We'll divide this equation by 2, and we get that X equals to 1 unit. Here X equals to 1 unit. That is to say, AD that is equal to X, it is equal to 1 unit. And DO that is also equals to X, this is also equals to 1 unit. Okay. So in the next step, we will complete the quarter circle to a circle. So after we completed the quarter circle to a circle, we'll extend the radius BO by a straight line until it touches the circle. We'll define the touching point of the extended BO and the circle is point P. Actually, we extended the straight line BO, that is the radius. It is a straight line because it is the radius of the quarter circle, that is also the radius of the circle, therefore it is a straight line. And when you extend a straight line by a straight line, the result, that is PB, must be a straight line. So PB is a straight line, and PB passes for the center of this circle, therefore PB is the diameter of the circle. PB is the diameter of a circle because any chord that passes for the center of the circle, it is defined as the diameter of the circle. So PB is the diameter of the circle. PB is a diameter, it is absolutely a straight line. Okay? And we know that the sum of the angles on one side of a straight line equals to 180 degrees. So if you focus on the upper side of the straight line PB at point O, then the sum of the angles here must be equal to 180 degrees. So which angles we have in the upper side of PB at O? Point O, we have 90 degrees plus angle AOP. 90 degrees plus angle AOP must be equal to 180 degrees. We'll subtract 90 degrees from this equation, and we get that the missing angle AOB equals to 90 degrees. So this angle equals to 90 degrees, it is a right angle. We will extend side CD by a straight line. Until it touches the circle. Okay? So by extending the straight line CD by straight line, we created peripheral angle. Suppose that this peripheral angle is angle BCX. We don't know where it touches the circle. Okay? So we have here angle BCX, it is a peripheral angle. Angle BCX is a peripheral angle, but we know for sure that the peripheral angle BCX equals to 90 degrees. And we have the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, and the diameter of the circle is PB. That is to say, when we extend side CD by a straight line, it must touch point P, because it rests on the diameter that is PB. That is to say, it must, when we extend the straight line CD, it must touch point P. Okay? Or it must pass point P. Okay? Therefore, we have here angle BCX that is equal to angle to 90 degrees. It is equal to actually to angle BCP. Why? Because it must rest on the diameter. In order that the right angle BCX will rest on the diameter, it must touch point P. Therefore, angle BCX, it is also angle BCP that rests on the diameter PB, because it is equal to 90 degrees. Okay? So here we have, we know that point O is the center of the circle, also the center of the quarter circle, and also the center of the circle. point P is the point of the circle itself. This is exactly the definition of a radius. That is to say, PO is the radius of this circle that is equal to 2 units. Okay? So if you focus on the right triangle POD, in the right triangle POD, we'll implement the Pythagoras theorem on the right triangle POD. On the right triangle POD, according to the Pythagoras theorem, we get that by PT is the relation for Pythagoras theorem. Here the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PD, therefore the square of the hypotenuse is PD squared. And it is equal to DO squared plus PO squared. Okay, I repeat again, in the right triangle POD, PD squared equals to DO squared plus PO squared. So PD squared equals to DO squared. DO is 1, so DO squared is 1 squared, that is 1, plus PO squared. PO is 2, so PO squared is 2 squared, that is 4. So in conclusion, found out that PD squared equals to 1 plus 4, that is 5. Here we take a root out of this equation and we get that PD, the hypotenuse PD, equals to the square root of 5 units. PD equals to the square root of 5 units. In the next step, we'll implement the Pythagoras theorem on the right triangle DOB. In the right triangle DOB, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is dB, therefore the square of the hypotenuse is dB squared. That is equal to OD squared plus OB squared. Okay, in the right triangle DOB, according to the Pythagoras theorem, OB squared equals to OD squared plus, and DB squared equals to OD squared plus OB squared, so DB squared equals to OD squared. OD is 1, so OD squared is 1 squared, that is 1, plus OB squared. OB is 2, so OB squared is 2 squared, that is 4. So OB squared equals to 1 plus 4, that is 5. We will take out of this equation, and we will get that dB, the hypotenuse, equals to the square root of 5 units. dB, the hypotenuse dB, equals to the square root of 5 units. In the next step, we'll extend the radius AO by a straight line until it touches the circle at point Q. We'll define the touching point of the extended radius AO and the circle is point Q. Okay, O is the center of the circle. Q is a point on the circle itself. This is exactly the definition of a radius. OQ. So OQ is the radius of the circle that is equal to 2 units. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. So here, according to the new rule, it is actually not a new rule, but I've already mentioned this rule previously. So here we have this circle we have chord AB. This is chord AB. That intersects with chord CD. This is chord CD at point O. I'll repeat again. Chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Okay? AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have chord AQ that intersects with chord CP at point D. Again, I repeat again. Chord AQ intersects with chord PC at point D. I repeat again. Chord AQ intersects with chord PC at point D. Therefore, according to rule number 1, we will get that AD times DQ, AD times DQ equals to PD times DC. I'll repeat again. AD times DQ equals to PD times DC. Again, AD times DQ equals to PD times DC. AD is 1. DQ is 1 plus 2, that is 3, equals to PD is equal to 5 units, times DC is the missing 9 segment. So in conclusion, found out that according to rule number 1, this is according to rule number 1, of course, 3 equals to square root of 5 times DC. We'll divide this equation by square root of 5, and we'll get that DC, the missing 9 segment DC, equals to 3 over square root of 5 units. Okay, DC equals to 3 over square root of 5 units. Can I tell that DC equals to 3 over square root of 5 units? In the next step, we will implement the Pythagoras theorem on the blue right triangle, triangle DCB. This is the area that we are looking for, the area of this blue triangle. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is dB, therefore the square of the hypotenuse is dB squared. That is equal to dC squared plus CB squared. repeat again. In the right blue triangle, triangle DCB, according to the Pythagoras theorem, PT is the abbreviation for Pythagoras theorem. DB square equals to DC square plus CB square. So DB is square root of 5, so DB square is square root of 5 units. Square root of 5, that is 5, and it is equal to DC square. DC is 3 over square root of 5, so DC square is 9 over 5 plus CB square. So found out here that 5 equals to 9 over 5 plus CB square. We'll subtract 9 over 5 from this equation, and we find out that 5 minus 9 over 5 equals to CB square. Here we'll multiply 5 by 5, and then we'll divide it by 5 in order to have a common factor with this expression. And we'll get here that 25 minus 9 over 5 equals to CB square. 25 minus 9 is 16, so it is 16 over 5. That is equal to CB square. Here we take a root out of this equation, and we get that CB equals to the square root of 16, that is 4 over square root of 5. So we found out that CB equals to 4 over square root of 5. Now it is very easy to find out the area of the blue right triangle, triangle DCB. The area of DCB, the right triangle DCB, will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Repeat again. The area that we are looking for, that is the area of the blue triangle, triangle DCB, equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So here we have already found out that DC equals to 3 over square root of 5 units, times CB, that is 4 over square root of 5 units, over 2. So here we have 4 times 3 times 4 is 12. Square root of 5 times square root of 5 is 5, over 2. 12 over 2 is 6. And the denominator we have only 5 left. So in conclusion, the area of the blue right triangle, triangle DCB, will be equal to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. So we finished with the first method. In the next step I will present to you the second method. We have already found out that here, this angle A or B, in the first method, that it is equals to 90 degrees, because of the fact that it is a quarter circle. O is the center of the quarter circle. AD equals to 1 unit. DT O equals also to 1 unit according to the first method. We'll complete the quarter circle to a semicircle. We will define the touching point of the extended radius BO if the semicircle is point P. PO is the radius of the circle that is equal to 2 units because of the fact that line segment PO starts from the center of the circle, that is to say from point O, and ends at point P, that is the point of the semicircle itself. We will join point C and D together by a straight line. We will extend line segment CD until it touches the circle, and suppose that the extended line segment CD touches the circle at point X. So we have here angle BCX, that is absolutely, it is equal to 90 degrees because it is given as the question that angle BCX equals to 90 degrees. Okay? But we know, so here we created peripheral angle BCX that is equal to 90 degrees. And any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. That is to say PB, that is to say angle BCX must be equal to angle BCP, because it must rest on the diameter of the circle, and the diameter of the circle or semicircle is BP. Therefore, it must touch point P. So actually angle BCX equals to angle BCP. Okay? Because this angle, that is a peripheral angle that is equal to 90 degrees, must rest on the diameter of the circle. And the diameter of this circle is PB. That is to say, when we extend line segment CD by a straight line, it must touch point P. Otherwise, it will not rest on the diameter of the circle. And according to the rule that I mentioned, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. That is to say, when we extend the straight line CD, it must touch point P. That is to say, angle BCX equals to angle BCP, that is equal to 90 degrees. Okay, and we have already found out in the first method that angle DOP equals to 90 degrees. We have already found out that in the right triangle POD, the hypotenuse PD equals to the square root of 5 units. And we have already found out that in the right triangle DOB, the hypotenuse DB equals to square root of 5 units. Okay? So here we will define angle OPDPO as theta. If angle DPO equals to theta, and triangle DOP is the right triangle, so this angle DOP equals to 90 degrees. This angle equals to theta, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle DOP to 180 degrees. This angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. So this angle ODP must be equal to 90 degrees minus theta. And exactly for the same reason, if we focus on the right triangle PCB, this angle equals to theta. This angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta, exactly for the same reason. In the next step, we will prove that the right triangle POD is similar to the right big triangle, triangle PCB. Okay, so I'll write it down. We'll prove that the small right triangle, triangle POD is similar to the big right triangle, triangle PCB. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So here, angle POD, this angle equals to angle PCB, this angle, and they are both equal to 90 degrees. So I repeat again, angle POD equals to angle PCB, and they are both equal to 90 degrees. In addition, we have this angle is a common angle that belongs to both triangles, so this angle equals to itself. So here angle OPD, equals to angle CPB, and it is equal to theta according to our definition. So here angle OPD equals to angle CPB equal to theta according to our definition. Finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So here, angle PDO equals to this angle that is actually angle PBC, and it is equal to 90 degrees minus theta. Repeat again, angle POD equals to angle PBC, and they are both equal to 90 degrees minus theta. So we prove that all three angles of triangle POD are equal to all three angles of triangle PBC, therefore triangle POD is similar, this is the sign of similar, to triangle PCB according to angle similarity rule. Okay, and from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We'll conclude that PD over PB equals to DO over CB, and it is equal to PO over PC. I repeat again, from the fact that the two right triangles are similar to each other, we conclude that PD over PB equals to DO over CB equals to PO over PC. Okay? So here, PD equals to a square root of 5 units over PB equals to 2 plus 2, that is 4. And it is equal to DO, that is 1, over CB, that is the missing line segment, and it is equal to PO. PO is 2 over PC. PC is square root of 5 units plus DC. So in conclusion, we found out that square root of 5 over 4 equals to 1 over CB, that is equal to 2 over square root of 5 plus DC. Okay, so here we get from this equation the first equation, that square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation, equation number 1, and we get that according to equation number 1, CB times square root of 5 equals to 4. We divide this equation by square root of 5, and we get that according to equation number 1, CB equals to 4 over square root of 5 units. So we found here that CB equals to 4 over square root of 5 units. In the next step, we will create the second equation. Here, the first expression equals to the third equation. So the first to the third expression, that is to say, square root of 5 over 4 square root of 5 over 4 equals to 2 over square root of 5 plus DC. Okay, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we cross multiply this equation, equation number 2, and we get that square root of 5 times square root of 5 plus DC equals to 2 times 4, that is 8. Here we will open the brackets on this side of equation number 2, and we get that square root of 5 times square root of 5 is 5, plus square root of 5 times DC equals to 8. Here we subtract 5 from this equation, equation number 2, and we get that square root of 5 times DC equals to 3. Here we will divide this equation by square root of 5, and we get that according to equation number 2, DC equals to 3 over square root of 5. So we found out that DC equals to 3 over square root of 5. Here, DC equals to 3 over square root of 5. Now the area of the blue right triangle DCB will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Repeat again, the area of the blue right triangle DCB equals to DC, that is the base, times the height, that is CB, over 2. So DC equals to 3 over square root of 5 units, times CB is 4 over square root of 5 units, all divided by 2. So here we got that 3 times 4 is 12, square root of 5 times square root of 5 is 5, over 2. 12 over 2 is 6, so in the denominator we left only with 5. So in conclusion, we found out that the area of the blue right triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. We finish with the second method. In the next step I will summarize the lecture. Okay. We start with the first question, of course. In the first question, we have triangle, the right triangle, triangle ABC, and inside the right triangle ABC we have this circle. Actually, this circle is inscribed by the right triangle ABC. Side AB equals to 8 units. Angle ABC equals to 90 degrees, and we want to find out the radius of this circle that is inscribed by the right triangle, triangle ABC. Okay, so first of all, we define side BC as A. We define side AC that is the hypotenuse of triangle ABC as B. And then we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AB square plus BC square. So here, AC equals to B according to our definition. So AC square is B square, and it is equal to AB square. AB is 8, so AB square is 8 squared, that is 64, plus BC square. BC equals to A according to our definition, so BC square is A square. So in conclusion, we found out that according to equation number 1, B square equals to 64 plus A square. We subtracted A square from this equation, equation number 1, and found out that B square minus A square equals to 64. According to the algebraic identity, B square minus A square equals to B plus A times B minus A, that is equal to 64. So here, BC and AC are integers, it is given as the question. So BC equals to A and AC equals to B. That is to say, AB are integers. And because of the fact that A and B are the length of the sides of the right triangle, so as length, they must be a positive number. So we know that AB are both integers and also positive. So we can conclude from it that A and B are positive integers. So again, A and B are positive integers. So according to equation number 1, we found out that here actually according to equation number 1, B plus A times B minus A equals to 64. But because of the fact that A and B are positive integers, it means that B plus A must be greater than B minus A. Again, here, B plus A must be greater than B minus A. And because of the fact that AC equals to B and B is the hypotenuse, as the hypotenuse, B must be greater than A. This is perpendicular. So B is greater than A, we subtract B from this equality, we subtract A from this equality, and we got that b minus a is greater than 0. So b minus a is a positive. So b is a positive integer and a is a positive integer. So b minus a, that is a positive, it must be a positive integer. So b minus a is a positive integer, and b is a positive integer, a is a positive integer. Therefore, b plus a must be also a positive integer. Okay, so we found out that b plus a is a positive integer, and b minus a is also a positive integer. So, what options we have here, according to the equation number 1, b plus a times b minus a equals to 64. So we have to find out two positive integers that if we multiply one by each other, we'll get 64. What options we have here? There are not a lot of options. There are few options that if we multiply two positive integers by each other, we will get 64. What are the options we have here? The first option is 1 times 64, that is 64. The second option is 2 times 32, that is also 64. The third option is that 4 times 16, that is 64. The fourth option, that is 8 times 8, that is 64. The fifth option, that is 16 times 4, that is 64. The sixth option is 32 times 2 is 64. And the last option is that 64 times 1 equals to 64. So, first of all, because of the fact that b plus a must be greater than b minus a, so here 1 is not greater than 64, so this option is not good. 2 is not greater than 32, therefore this option is not good. 4 is not greater than 16, therefore this option is not good. And 8 equals to 8, it is not greater than 8, so this option is not good. So we left only with this option. 16 is greater than 4, so this is a good option. 32 is also greater than 2, therefore it is a good option. And 64 is also greater than 1, that is to say it is also a good option. Then we actually added b plus a to b minus a in order to find out what results we will get here. Here we added b plus a to b minus a. b plus b is 2b and a minus a is 0. So we found out that when we add the two numbers together, we must get an even number, because 2b is an even number, because b is a positive integer, and when you multiply positive integer by 2, we will get a positive, an even number. That is to say, we can only take the options of the even numbers. That is to say, if we add the two numbers together, we must get an even number. So we'll see which options we have here, that when we add the two numbers together, we'll get a positive, an even number. 16 plus 4 is 20, it is an even number, so it is good option. 32 plus 2 is 34, that is an even number, it is good option. But 64 plus 1 is 65, that is an odd number, that is to say it is not a good option. So we left only with those two options. So the first option is that b plus a equals to 16 and b minus a equals to 4. This is the first option, and the second option is that b plus a equals to 32. and b minus a equals to 2. So here, if we add the two equations together, b plus b is 2b and a minus a is 0. So here 2b, we have 2b on this side of the equation, and the other side of the equation we have 16 plus 4, that is 20. So in conclusion, we found out that 2b equals to 20. We divided this equation by 2, and we got that b equals to 20 over 2 is 10. So we found out that the hypotenuse b equals to 10 units. Here we have b plus a equals to 16. We subtracted b from this equation and found out that a equals to 16 minus b. That is to say, a equals to 16 minus b and b is 10. So a equals to 16 minus 10, that is 6. So we found out that a equals to 6 units and b equals to 10 units. Okay? So the hypotenuse equals to 10 units and the perpendicular equals to 6 units. And the other perpendicular is 8 units in the right triangle ABC. And according to the second solution, here b plus a is 32 and b minus a is 2. We will add the two equations together and we get that b plus b is 2b and a minus a is 0. So we got that 2b equals to 32 plus 2, that is 34. We divided this equation by 2 and we got that b equals to 34 over 2, that is 17. So the hypotenuse b equals to 17 and b plus a equals to 32. We subtracted b from this equation and found out that a equals to 32 minus b. Here a equals to 32 minus b and b is 17, so a equals to 32, that is minus b, that is 17. So a equals to 32 minus 17, that is 15. So in conclusion, according to the second solution, we found out that the hypotenuse a equals to 15, the perpendicular a equals to 15 and the hypotenuse b equals to 17 units. So here, then actually we have to find out the radius of the circle that is described by triangle ABC. The first triangle that we have here, AB equals to 8 units, BC equals to 6 units, and the hypotenuse equals to 10 units. And according to the second solution, the hypotenuse AC equals to 17 units, AB equals to 8 units, and BC equals to 15 units. So here, what is the radius of this circle that is described by a right triangle, triangle ABC? So here we do triangle ABC that could be any triangle. Okay, here side AB of triangle ABC equals to A units, side BC equals to B units, and side AC equals to C units according to our definition. Inside the right triangle, we have this circle that is described by triangle ABC. And here we actually have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius known to its point of tendency. So here, those two angles must be equal to 90 degrees. And here we have a tangent to a circle is perpendicular to the radius known to its point of tendency. Here, OM, the radius OM is known to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, and here we have this angle that is equal to 90 degrees. According to what is given as the question, it is a right angle, so we have here 1, 2, 3 right angles in quadrilateral B, M, and O, and according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, this angle must be also equal to 90 degrees. So inside quadrilateral M, O, B, N, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. And we know that the opposite sides of a rectangle are equal to each other, that is to say MO equals to BN. But MO equals to R, so BN also must be equal to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we will get that ON equals to MB. But ON equals to R. Therefore, MB must be also equal to R. So we found out that quadrilateral M of BN, it is not a rectangle but a square. So here, what is the length of AM? AM equals to AB minus MB. AM equals to AB minus MB. AB is A and MB is R. So in conclusion, AM equals to A minus R. Then we found out the length of BC. The length of NC. NC equals to BC minus BN. BC minus BN equals to NC. BC is B and NC is R. So in conclusion, NC equals to B minus R. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So if we focus on the right, on the common external point, point A, we have two tangents to this circle, tangent AM and tangent AZ. According to rule number 2, they are equal to each other. AM equals to AZ, but AM equals to A minus R. We have already found out that AM equals to A minus R, therefore AZ must be also equal to A minus R. Then we focus on the common external point, point C. From the common external point C, we have two tangents to this circle, tangent CN and tangent here, tangent CZ. And according to rule number 2, CN equals to CZ. But CN equals to B minus R, therefore CZ also must be equal to B minus R. Why? Because they are equal to each other. So, what is the length of the hypotenuse AC? According to our definition, the hypotenuse AC equals to C. Okay? From the drawing, it is very easy to see that AC equals to AZ plus ZC. AC equals to AZ plus ZC, but AZ equals to A minus R, and ZC equals to B minus R, and AC equals to C according to our definition. So in conclusion, I found out that C equals to A minus R plus B minus R. So C equals to A plus B minus 2R. We divided, we added 2R to this equation and found out that 2R plus C equals to A plus B. Then we subtracted C from this equation and found out that 2R equals to A plus B minus C. Here we divided this equation by 2 and found out that the radius that we are looking for, the radius of this circle that is inscribed by triangle ABC equals to A plus B, that is the sum of its perpendicular, the sum of the perpendiculars of the right triangle minus the C that is the hypotenuse of the triangle over 2. Okay, so we can use this formula in order to find out the radius of this circle that is inscribed by triangle ABC. According to this formula, the radius R equals to A plus B minus C over 2. A plus B is 8 plus 6 minus the hypotenuse that is 10 over 2. 10 plus 6 is 14, 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle that is described by the right triangle ABC equals to 2 units. And according to the second solution, we have here this right triangle, and R equals to the sum of its perpendiculars, that is 8 plus 15, minus the hypotenuse that is 17 over 2. 10 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So here we actually found out two solutions to the question. The first solution is that R equals to the radius of the circle that is described by the right triangle ABC. The radius of this circle equals to either 2 units or 3 units. Okay, so we finish with the first question. In the next step, I will present to you the second question, and actually solve the second question in 2 different methods. And here we have actually we have a quarter circle. Inside this quarter circle we have triangle ABC, triangle PCB, and we want to find out the area of this triangle. We know that OB equals to 2 units, and angle BCD equals to 90 degrees, AD equals to DO, and we want to find out the area of the blue right triangle. Okay, and we actually, because of the fact that AOB is a quarter circle, this angle equals to 90 degrees, O is the center of the circle, and O, so here AO is also the radius of the quarter circle, so AO equals to OB equals to 2 units. That is the radius of the quarter circle. And here we defined AD as x, so OD must be also equal to x because they are equal to each other. So x plus x equals to AO, that is 2 units. X plus x equals to AO, that is 2 units. So 2x equals to 2. We divided this equation by 2 and found out that x equals to 1. So AO equals to DO equals to 1. Okay, then in the right triangle, triangle APD, actually we completed the quarter circle to a circle, and here O is the center of the circle, P is the point of the circle itself, therefore PO equals to the radius of the circle, that is 2 units. Okay, then this angle, we know that PB is the diameter of the circle because of the fact that it passes through point O, that is the center of the circle. Therefore PB is a straight line, and we know that the sum of the angles on one side of the straight line equals to 180 degrees, and this angle equals to 90 degrees. This angle must be also equal to 90 degrees. So in the right triangle, triangle POD, we implemented the Pythagoras theorem. Therefore, according to the Pythagoras theorem, if this side is 2 and this side is 1, this side, the hypotenuse must be equal to square root of 5 units. The same thing is true here. In the right triangle DOB, this side equals to 1, side OB equals to 2, therefore the hypotenuse must be equal to the square root of 5 units. Okay? And then we extended side AO by straight line until it touches the circle at point Q. O is the center of the circle, Q is the point of the circle itself, therefore OQ is the radius of the circle, that is equal to 2 units. Then we implemented rule number 1, number drawing. According to rule number 1, if chord AB intersects with chord CD at point O, then point O is the intersection point of chord AB with chord CD, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We implemented rule number 1 in our drawing because in our drawing we have chord AQ that intersects with chord CP at point D. Therefore, here AD times DQ equals to PD times DC. AD times DQ equals to PD times DC, according to rule number 1. PD is 1, this is DC. Here, DC is 1 plus 2, that is 3. DC is 3. PD is square root of 5 units. And DC is the missing line segment. So in conclusion, we found out that 3 equals to square root of 5 times DC. We divided this equation by square root of 5 and we found out that DC equals to 3 over square root of 5 units. Found out that DC equals to 3 over square root of 5 units. Then we implemented the Pythagoras theorem on the right triangle DCB. Here, dB square equals to DC square plus BC square. In the right triangle DCB, dB square equals to DC square plus CB square. According to the Pythagoras theorem, dB is equal to 5, so dB square is equal to 5 squared, that is 5. And it is equal to DC square. DC is 3 over square root of 5, therefore DC square is 9 over 5 plus CB square. We subtracted 9 over 5 or 9/5 from this equation. We found out that 5 minus 9/5 equals to CB square. We multiplied 5 by 5 and then we divided by 5 in order to overcome a factor with this expression. We found out that 25 minus 9 over 5 equals to CB square, so 25 minus 9 is 16. So in conclusion, we found out that CB square equals to 16 over 5. We took out of this equation and we found out that CB equals to square root of 16 is 4 over square root of 5. So CB equals to 4 over square root of 5. And we already found out that CD equals to 3 over square root of 5. Now it is very easy to find out the area of the blue right triangle, triangle DCB. It is equal to the base of the triangle, that is DC, times the height of the base, that is CB over 2. The base is DC times the height of the base, that is CB over 2. DC is 3 over square root of 5 units. CB is 4 over square root of 5 units, all divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5 times 2. 12 over 2 is 6, and the denominator we left only with 5. So in conclusion, we found out that the area of the blue white triangle, triangle DCB equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. We finished with the first method. Then I presented to you how to find out the area of the blue white triangle, triangle DCB according to the second method. Here, this is a quarter circle AOB, therefore this angle equals to 90 degrees. OB is the radius, that is 2. We have already found out that the first method that AD equals to 1, DC also equals to 1. We extended the quarter circle to a semicircle. Then we extended BO by certain until it touches the circle at point, the semicircle at point B. O is the center of the circle, semicircle. P is the point of the semicircle itself. Therefore, PO is the radius, that is 2. Okay. Then, according to the first method, this angle equals to 90 degrees. And PD, the hypotenuse PD equals to the square root of 5 units. And the hypotenuse PD in the right triangle DOB also equals to square root of 5 units. Okay. Then, actually, in the right triangle POD, this angle equals to 90 degrees. We define this angle at theta, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle POD to 180 degrees. This angle must be equal to 90 degrees minus theta. The same rule, the same thing is true in the right triangle PCB. This angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta. Then we proved that the right big triangle PCB is similar to the right small triangle, triangle POD. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Okay, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And this angle, it is a common angle that belongs to both triangles, so this angle equals to itself. In conclusion, we found out that all the angles of triangle PCB are equal to all the angles of triangle POD, therefore those two triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides, that PD over PB equals to DC over CB equals to PO over PC. PD is equal to 5 over PD is equal to 5, PB is 4, DO is 1, and CB is the missing 9 segment. PO is 2, and PC is equal to 5 plus DC. Again, PC is equal to 5 plus DC. Okay, from this big equation we derive the first equation, that's equal to 5 over 4 equals to 1 over CB. We could multiply this equation and found out that CB times equal to 5 equals to 4. We divided this equation by square root of 5 and found out that CB equals to 4 over square root of 5 units. Here CB equals to 4 over 5 square units. Then we created a second equation from this equation. Here 4 over square root of 5 equals to 2 over square root of 5 plus DC. Okay, here 4 over square root of 5 equals to 2 over square root of 5 plus DC. We could multiply this equation number 2, and found out that square root of 5 times square root of 5 plus DC equals to 4 times 2, that is 8. We open the brackets on this side of the equation number 2 and found out that square root of 5 times square root of 5 is 5, plus square root of 5 times DC equals to 8. We subtracted 5 from this equation number 2, and found out that square root of 5 times DC equals to 8 minus 3, that is 8 minus 5, that is 3. We divided this equation number 2 by square root of 5 and found out that DC equals to 3 over square root of 5 units. Here DC equals to 3 over square root of 5 units. Now it is very easy to find out the area of this blue right triangle. It will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Again, the base DC times the height to the base, that is CB, over 2. DC equals to 3 over square root of 5 units. CB equals to 4 over square root of 5 units, all divided by 2. 3 times 4 is 12, and square root of 5 times square root of 5 is 5, times 2. 12 over 2 is 6, and then the denominator we left only with 5. So in conclusion, the area of the blue right triangle, triangle DCB, this right triangle DCB equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. So in both methods we arrive to the same result. Okay, thank you very much.